Hello everybody, I'm just going to give you a quick rundown on this multiple regression homework assignment. And so now it looks like you're going to be doing the assumptions. All right, give me a second before I read this. Standard multiple regression. The DV is salary, everything else is an IV. Variance, predictors. Okay, I know what to do. Number one, run a standard or multiple regression to see which variables predict the model's salary. So here we go. So I'm going to go to analyze regression. Where's regression? Regression, linear. The DV is salary, and we want the three others to be the IVs, predictors. And these. Durbin Watson checks autocorrelation or independence of errors. Plots. This is your Z from your predictors, and it always goes down on the bottom. Z residuals goes on top. Now, I'm going to show you some stuff that the good Dr. Armovich might do differently, okay? So, in other words, follow him. This guy never misses. He's too smart for humans. So, whatever he says goes. So, if my stuff is different, he disagrees, I'm going to tell you right now, just go with him. He knows this stuff better than anybody. Click continue. So, again, Z-pred, these are predicted Z-scores. They go on the X column down here. And the Z residuals, they go on your Y column. So the residuals are always your Y variable. Click OK. And what else we got? Now, I don't know how he teaches you about multivariate distance checkers. I strictly use the Mahalanobis because it's the easiest to use. There are others, so find out which one he wants you to use. And I believe he wants you, I read in here somewhere that he wants you to look at the standardized residuals. So we will. I don't know if we're going to use that right now. But let's hit continue down here at the bottom. And I think the rest of this is okay. And we're just going to hit okay. Get up there, you. Okay, just hit okay. And we're going to get an output. So here's the output. Let me look at the first one, model summary. It gives you your R squared. Remember, this is the percent of the variance of the DV that can be explained by these predictors or by this model. And this is considered strong, right? So this is actually a good predicting model. And it was significant, right? This is a significant F change. And this basically should agree with the ANOVA, which is coming up here in a second. So let's jump down there. There's the ANOVA. It is significant. Therefore, this regression model is significant. In other words, at least one of your predictor variables, beauty, years, or age, is a good predictor of how much a person's going to make with their salary. So let's actually read the questions. And, you know, this tells you who's the strongest predictor. And I go by beta weights. Dr. Armovich tends to go by semi-partials, but they should agree. So the strongest beta weight is by far age, and it's the same with semi-partials. By far, it's the strongest. Okay, so age is number one, years is number two. You'll notice beauty is not a significant predictor. Okay, so we're going to leave beauty out of this. And let's start answering questions. Variance explains statistical significance of the model. Okay, so he's not addressing any of the assumptions yet. So there was a significant regression model, according to the ANOVA, and we just write it up like this. Using a critical alpha of 0.05, F, 3, 227 equals 17.003. And what this literally means is that you can explain 17 times as much of the data can be targeted with this regression model as the other one is the error model. Okay, so that, remember, ANOVA is between group divided by within group. So this one with the regression model, you're comparing sum of squares of the regression, that's your numerator, over sum of squares of the residual. And remember, residual means error. So this one is a real strong model, significant, and you can explain about 18.4% of the variance of the DV, which is the salaries. And it's large, and it's R squared. And I did this already. Both age and years are significant predictors, but beauty is not. And we already did that too. Okay. Here is your effect size table. I'm going to keep showing you this, but this is the R squared that SPSS puts out. And ours is 18.43. I'm sorry. Yeah. 18%, which is to the right of this. So it's a large effect size, which means that you can believe this model. All right. Individual predictors. So who's the king? Age is the king. Who's number 2? Years is number 2. Beauty don't work. You might as well cross that thing out. Goodbye, Mr. Bond. Okay. Beauty is not a significant predictor, but age is number 1, years is number 2. And again, you can either look at the beta weights or the parts, which is actually semi-partial. But they are significant. Make sure they're significant. So again, age is the best predictor, years is the second best. So now we're going to check the assumptions. This is the one that takes forever. Seriously, folks, the more complicated a statistics test becomes, the more difficult it is to check the assumptions. It literally takes you more time to check the assumptions than it does to run a test. But the assumptions are there for a reason. You have to meet them, because if they're violated, it can turn your test into oatmeal, and not good oatmeal, with icky, lumpy, undercooked chunks. Ugh. All right, back to work. So here are the assumptions of a multiple regression. Where did I get these from? If you don't know that answer, shame, I say shame on you. I went to the Moodles, and you should finish this sentence. You know that you went to the Moodle 3, because anything with correlations and regressions is in Moodle 3, and I simply waited and waited and waited and waited. It literally took me 30 seconds to get this page open, but I'm not going to knock anybody. Not yet. So this is Hawk 3. I'm going to scroll down to, this is regressions part 1, and it's got it right there. Assumptions for a multiple regression. Shkabam. Shkabam, there they are, etc., etc. So back to our web sheet. So additivity, I found out the hard way that additivity is what some people call multicollinearity. Multicollinearity is where two IVs are more strongly related to each other than they are with a DV, and that can cause you some serious problems. I am here to tell you. Okay. So again, I've never seen that before in additivity in my 20 plus years of doing statistics. So I'm thinking, doctor, your teacher might be from like Canada or something. You might want to ask him. Okay, so additivity is the same as multicollinearity, and it shows up as collinearity in SPSS. All right, so what we're going to do is we're going to do the check. So to check for additivity, we're going to go to the collinearity box. It's in the coefficients box. And both of these are tests for multicollinearity. Here is the rule. If this number here is less than 0.1, which two of them are, you have violated the assumption of multicollinearity. Same with this, BIF. If these numbers are greater than 10, you have violated that assumption. So these two, your only two significant predictors, are both strongly correlated with each other, too strongly correlated with each other. That's what this means. So again, if the tolerance is less than 0.1 or the BIF is greater than 10, that means you got multicollinearity. So you violated that one, okay? Linearity. I don't know how deeply he wants to go. Some teachers are okay with a correlation table, right? So we're expecting a linear relationship between the DV and each of the IVs. So that's this row of numbers right there. And since none of them are 0, I'm going to assume that the assumption of linearity was not violated, right? This is big, this is big, this is not so big, but it's not 0. Okay, so I'm not going to worry about that. There are other methods. Some teachers like the matrix box. This one's kind of a pain in the butt, but I guess I should show you how to do that. Hold on. And you're about to find out my kryptonite. I've never been very good at the graphs, but let's give it a shot. Graphs, legacy. We're going to go down here to scatter plot, scatter dot. And what happened? Let's try this again. We went to graphs, legacy, scatter dot. Oh, there it is. Please hold. And we did the matrix. That means there's a lot of little graphs on the same thing. We used sine. And so our matrix, we want, it's going to be salary. I'm going to pause this for a second. I always forget how to do this, but what you do is you stick all of your IVs and DVs, significant DVs, just stick all your variables into the same box here. And then once you get this bottom, once this blue box goes blue instead of ungray, that means it's ready to go. And the rest of it's pretty self-explanatory. It knows how to make its own little boxes. So these are the bar graphs between salary and salary, so that's blank. Salary and age in years, salary and attractiveness. Again, they should be some kind of best fit line. You should be able to see the pattern of a best fit line. Let's see if we can put one in there. We're going to open up the chart editor by double clicking on that bad boy. We're going to click there. We're just going to put a best fit line. It should do them all. And take a while. There they are. Boom. So the only one I'm worried about is this one, because you do not want a horizontal line. That means when one value changes on the x, the y value doesn't change for crap. But the rest of them seem to do that. Okay, so that's enough about linearity. It is boring me like crazy. Let's go to the next one. So we did additivity. That's called multicollinearity. It violated. We're assuming that it's linear. That didn't violate. Normality. So, normality. How can I put this? Normality is actually multivariate normality. It's not univariate normality. That a lot of students get that thing mixed up. But we're talking about a multivariate normality. So in this example, if somebody was high in age, high in years as a model, high in attractiveness, that would make them a multivariate outlier because they're really, really high in more than one of the variables. So the test we use for that is called the Mahalanobis. Oh, wait a minute. Before I get there, I forgot. I went on and on and on about this linearity thing. So I did a individual scatter plot for so here's the first IV, age, against the DV. There's the second IV, years as a model, against the DV. And here's the third one, attractiveness, against the DV. And again, because they're not flat lines, that means it did not violate the assumption of linearity. So enough of that. Ugh. So again, back to univariate normality. I'm sorry. Multivariate normality. Univariate normality, that means one variable. That's what univariate means. That is not an issue here. We're not looking for that. We're looking at multivariate. So what I use is the Mahalanobis critical distance calculator. And that is one of the boxes there. And there it is. So out of our data set, our maximum is 13.345. Say that again. Our maximum distance from our data set is 13.345. So now we have to go back to the calculator. Hold on. Which you can use. There's a couple of them in here somewhere. You can just download it. I suggest you download it and put it on your computer forever. There's one right there. So just download it, open it up. Please hold. And this is a spreadsheet that's going to calculate our critical Mahalanobis distance value. So our sample size is what? 231. And K is the number of predictors, and we got 3. And click OK. So in other words, if we had any data set that had a Mahalanobis distance of greater than 18.613, we would consider that guy a significant multivariate outlier. I'll say that again. If we have anybody in our data set that has a Mahalanobis critical distance value of greater than 18.6, it would be considered an outlier. But thanks to the miracle of science, we know what the maximum is already. The maximum is only 13. So all that means is no multivariate outliers. That's good news. Moving on to homogeneity variance. Homogeneity variance, what we call that in a multiple regression model, is called homoscedasticity. So now, without losing sleep, homoscedasticity subsumes homogeneity variance. In other words, homogeneity variance is part of homoscedasticity. So to check for homoscedasticity, man, that is a killer word. We're going to use what we call a Lois line, right? Like Superman's girlfriend, Lois Lane, the Lois line. And I'll just show you. Remember that Z pred and Z residual thing? That's this. That's this box here, right? So the bottom x-axis is the regression standardized predicted value, and then your y value is your regression standardized residuals, okay? So what I did was, let me pull it over to the real one here. So back to the data sheet. And if you missed it on this video, go back to Hawk 3. I guarantee you, man, everything that I've done here, I have 5 different times up there. So this is that. You'll notice there's no lines on it. So what you do is you double click it. You bring up the chart editor. You're going to put in a best fit line. And then it pulls up the box, and you're going to pull up what we call the lowest line. And click apply. So what that does is it puts in what a lowest line does, and what that means is it checks for homoscedasticity. In other words, the evenness of these data residuals, how evenly are they spread out? So if they were perfectly spread out, in other words, if this thing was perfectly homoscedastic, this line, the lowest line, would be completely horizontal and completely straight. It would be a straight horizontal line. And it's not quite there. It is relatively straight, but you'll notice it goes downhill. So I'm going to call it that the data minorly violates the assumption of homoscedasticity. In other words, the spread of the residuals aren't 100% perfect across the scales of your variables, which, it's not a deal breaker or anything, but just keep moving. All right, please hold. That's what that is. Independence of errors. That's what we call autocorrelation. Okay, so autocorrelation is checked using what we call the Durbin-Watson test, and that's in your model summary box. And for our problem, it's 2.056. And, the short version is you want a Durbin-Watson value of somewhere around 2, which is practically perfect. Now, I've read books where it says it should be between 1.5 and 2.5. I've read other books where it says it should be between 1.8 and 2.2. And basically what it means is that you don't have any parallel going on. In other words, you got 2 IVs where they seem to be, one is copying the other. That's bad. And that's not what's going on here, because your Durbin-Watson checked for independence of, what does he call it? Independence of observation? No, independence of samples, errors, is not happening, right? So we call this autocorrelation. And E, based on the answers in the previous question, is this a trustworthy model? I would consider it a semi-dependable model. It's not perfect by far because it violates homoscedasticity a little bit. It violates multicollinearity, or what he calls additivity, by the only two significant predictors. So this part right here is going to become problematic, I guarantee you. And I would be a little bit suspicious of the output. And if I was investing my own personal money into this model, I would not. All right, let's go to number 3. I'm not sure what he's asking in question 3, right? He talks about outliers. But again, when you're dealing with outliers in a regression model, you're only talking about multivariate outliers, not univariate outliers, okay? So, and he gives you a hint. Request standardized residuals outside of 2. What percent of your data lie outside of 2 and 2.5 standard deviations? That's a damn good question. So I'm going to go ahead and look it up here. I think I did check that box. Give me a second. Hold on. And there's a standardized residual, right? Our lowest was negative 1.7. That's not bad. Our maximum was 4.62, which was high. So I'm kind of at a loss. I wasn't sure exactly what he's asking for here. I did go to each individual IV, which is the univariate side, which I don't think is the right thing to do, but maybe he has something that I am not sure about. But anyway, yes, there are right around 6 individual pieces of data per IV that have that their residuals are too high. Right? They're greater than 2. But, 6 out of 231 is what, about 2.5%, which is not a deal breaker. So it looks like, anything under 5% you can live with. So it looks like that as far as I could tell, again, I'm not taking any responsibility for this question because, again, I'm not sure what he is asking. So one of you guys is going to have to tell me, because I gotta start teaching this stuff the way he teaches it, because I'm drawing a blank here. But moving on. So we have the standard residual right there, right? Boom, boom, boom. And we did that already. So multicollinearity, this thing violates the assumption of multicollinearity, or what he calls additivity. And we look at the collinearity stats for that, either the tolerance or the VIF. And yes, violated them both here and violated them both here, so they're violated. So he wants to know what you think about this, and I'm telling you, these discoveries, especially this one, multicollinearity or additivity, it weakens this model, right? So the more assumptions that are violated, the more that your validity and reliability from your model are also weakened. So this thing is, the air is getting let out of it. Pretty soon it's going to be flat, like a flat tire. So what are the potential solutions to you? And you could delete those outliers, the univariate outliers that I found, but I don't recommend that because I don't do that. So I'm not going to worry about that. The second thing is I'm going to check to see what the relationship is between age and years. Because if they're too strongly correlated, you got to do something. So I'm going to go to Analyze, Correlate, Bivariate, and it was age and years. I'm assuming that these two are going to be really, really strongly correlated, which is bad. It's bad in a regression model. Okay, don't need that. We don't need none of that stuff. And we're just going to click okie dokie. And please hold. Come on, you. All right, I'm looking right at it. So there it is. And it's okay. It's crazy. So the correlation between age and years is 0.955. That's bad news for your regression model. You can't use them both. This is what causes multicollinearity. It gives you misleading information. During the calculations, it's almost as if you're dividing by 0, which you do not want to do. So I would say, right, these two are too strongly correlated. And what you're supposed to do when you have one of those is you're supposed to drop one. So what I did was I reran the regression after dropping the variable of years. I just kicked years out, and I got this and I got this one, and the R squared only went down by what was it, 0.184, so 0.026. So it went down by about 200ths, which is very small, right? It dropped from 0.184 to about 0.159, and that is 0.025. So it dropped down to 25 thousandths of its strength, which is, like 2 cents worth. It's hardly anything at all. Again, when you have multicollinearity, you're supposed to drop one of your variables, usually the weaker of the two. And that's what I did. And what could you address the issue? What could you do to address the issues with the outliers? Does it help? I deleted them, and it did not help, period. Outlets. Outliers, you stupid computer. Hold on. Outliers. Right? It doesn't always help to delete outliers. You never know what's going to happen. It's the magic of statistics. But again, when I took out the outliers, it weakened the model further. The effect size went down to 0.066, which is between small and medium. So the more you check on the assumptions here, the weaker your model gets. So this is actually kind of a ho-hum model. You wouldn't. It's not that good, right? I've seen worse, but this is basically not a great model. I would not invest a lot of money. So again, this is the shortcut. I am not feeling well. I'm going home. So hope you guys all get a gist of this. MGZ out.